All right, here we are back again in chapter 12 of the DB2 course. Our discussion of merge join continues. There's some more bits that I would like to add to our discussion of merge join, and all of these are related to order, to either the order of the inputs that flow into the merge join, or the exploitation of the order of the output that is being produced by merge join. That can be, of course, of interest to subsequent operations in the query plan. So let's focus on ordering of inputs and outputs in merge join. First, sorted inputs. This is a requirement for merge join, and the system has to make sure that the plan is organized in such a way that once merge join comes into play, the inputs, both inputs, left and right table that flow into the merge join are sorted in some way. Of course, there is many ways how the system can make sure that this sort order is guaranteed. Well, it could, of course, introduce explicit sort plan operators below the merge join. So in general, we are looking at a constellation like this. The system has indeed decided to use merge join in a query plan. All right, and there will be two subplans below the merge join, of course, for the left and the right hand side input. And we are looking at these two subplans here. How can we make sure that these subplans generate their rows in the required order, in the order of actually the CL and CR columns, which are mentioned in the join criterion? Okay, of course, as I told you, these subplans could have subplan roots that are just explicit sort plan operators. These, of course, come with a cost, and the system considers this option, but it would rather not plan for an explicit sort. It would probably rather benefit or prefer the situation 2, where I can exploit an index scan on the left hand or right hand, or maybe on both inputs, index scans that deliver their rows in CL or CR order. So we would need an ordered index that is organized according to the join columns, either on the left hand or right hand side, or maybe on both inputs. That would be ideal and perfect. So in this case, the index scan would be used to just exploit the order, not to evaluate through conditions here. Okay. The input table itself may be clustered according to an index that is organized on the CL or CR column. So maybe the system knows that the heap file of the tables themselves are ordered. Then this, of course, would also be an acceptable order that can flow into the merge join. Of course, the ordering would have to be perfect. Okay, only then the correct functioning of the synchronized lockstep movement of the pointers in the left and right input will function correctly. Or the subplans below the merge join deliver the result in the required and desired order based on some other circumstances. Maybe the subplan in the left or right hand side plan is based on a merge join. Then this merge join will produce a guaranteed order, an interesting output order, and this could of course be exploited by this top level merge join here. So any subplan that already delivers its rows in such an interesting order that is interesting from the viewpoint of this merge join would be very welcome. It would actually lead to a no cost alternative. We would just exploit the order that is present anyway in the left or right input. All right. Well, I'm talking about, in option 2 here, I'm talking about index scan. And when I'm talking about index scan, I'm indeed talking about the Postgresql index scan, or maybe index only scan operator, as we also see in one example. You know that there is an alternative to index scan, that is the pair of bitmap index and heap scan. We have used these in our discussion of non-clustered B+tree indexes. I invite you to think about whether option 2 above could also be implemented and realized based on bitmap index and bitmap heap scans. And well, if you thought about it and you think that you've reached an answer, why not post in the forum? Post in the forum with the subject of, say, DB2 chapter 12. I think this is video 69, I guess. Well, I don't know for sure. Video number, and then question on slide 16. Will bitmap index heap scan also fit the bill of merge join? All right, and I'm looking forward to see your answer in the forum there. Okay, well, let's switch over to the terminal and let's see how Postgresql actually behaves when it comes to the generation or the exploitation of orders in the input of merge join. Okay. This would be our discussion here. So let's recall the one and many tables and their schemata. Okay, so this is the one table, ABC table, with just the primary key index on column A. All right, and the many side of things with, again, ABC columns. And well, this has the composite key with a concatenated B tree on the AC columns. We have seen these tables before. All right. So now let's consider equi-joins that could be evaluated using a merge join of these two tables. Okay, so one and many tables, these will be joined. This is the join condition. Let's look at the join columns real closely here. Okay, so the one side has a join column of C, and C is, let me check. Well, C is not an index supported column in the one table. Okay, so no index support to establish a C order on the rows of the one table here. Okay, but it's different on the many side. On the many side, the join column is the A column, and indeed the A column is the prefix of this concatenated B plus tree index. This index, the many AC index, could be scanned to deliver rows, the rows of the many table, in A order. This would just fit the bill as an input order for a merge join that could be exploited here. So let's try that. Let's see and look at the plan that is being proposed by Postgresql here. Right. Okay. Indeed, it's a merge join. It's a merge join based on the join condition that we have defined here. All right, this looks good to me. Okay, so now there must be two subplans that deliver their rows in A order on the many side and in C order on the one side. And this is indeed what we find. We find an index scan. We find an index scan on the many side. Indeed, this index scan can deliver rows of the many table in A order. And this is what we exploit in the top level merge join node here. No need for an extra sort operation here in the in this left hand side of the input. On the right hand side there is the one table. The one table and its join column C don't receive index support. So indeed what we see is a full sequential scan of the one table, right? And that is followed by a sort that will enforce a C order on the rows of this one table. You see it's an in-memory sort, it's an in-memory quick sort. The one table is small. Sorting that does not exceed the available working memory. We can do with an in-memory sort here, which is then fed into the merge join in the correct C order. All right, so that makes sense. It's perfect. All right. Well, one thing that you should note here is the result generation. Well, in the result here, we built a 3-column result, and we built on the B column of the many table. Unfortunately, the B column of the many table is not present in the AC index on the many side. It would be different if this would read m.c. Now, looking at the participating columns of the many table in this join, we would find the C column and the A column. Both of these are present in the AC index. And I think we could hope for an index-only scan in this particular situation on the many side. Okay, so this is the left-hand side, the right-hand side. This is still sorting the one table explicitly, but yes. Okay, so we are scanning the many table with the help of an index only scan. And of course, it really suffices to emit the columns A, C here, because that's all that's being used to produce the final output. Okay, so index only scan if possible, otherwise index scan. Let's switch back to B here. Nice. All right, for the next experiment, let's force Postgresql to use the merge join operation. I will switch off the contender hash join temporarily, just so that it doesn't interfere our experiments here. So no hash join for the next few minutes. All right, so let's see what's going on here. So this is a very similar situation, of equi-based join on one and many. Well, the one column again is participating using its C column, and there is no index support for that. The C column on the many side is present in the index. But well, it's only the secondary column in the index and can thus not be used to produce many rows in C order. There's also this A condition, this local condition on the many table with respect to the A column. I think this should be supported by an index scan. So we will probably see an index scan being used in this particular table, but not to produce rows in the needed merge join order. Okay, so let's see. Right. Okay, so indeed we are using merge join to evaluate this particular plan. It of course has the join condition here, and only that join condition as the merge condition inside the merge join. And then it has a left-hand side input and a right-hand side input. And both indeed are using explicit sort operators as we expected. Right. On the many side, we indeed can use the index to evaluate this local predicate here, but once the index scan has done its job, we will have to use explicit sorting. Okay, so this is the situation that we anticipated. But well, a very slight, a very subtle change in this particular query is indeed changing the underlying situation fundamentally. So let's scroll upwards here and see that I've just changed this less than sign into an equal sign here. Otherwise, everything stayed the same. In particular, the join condition stayed the same. So what's the situation now? Well, of course, the one table indeed no join and no index support here. Okay. How about index support on the many side? Well, with this condition, this equality condition, it's an equality condition on the A column. So this as index scan on the many side would focus on one particular A group. So in the concatenated B plus tree, we would focus on the one particular A group for A equals 2. Inside that A group, the C values are ordered in ascending fashion. Inside that A group, the C values are ordered in ascending fashion. But this is in fact the order that the merge join can use. All right, so it would be great if the merge join, if the entire query optimization logic of Postgresql would be aware of the fact that we are entering an A group here, and only inside that A group we would deliver rows in the interesting input order to merge join. Let's see whether Postgresql can indeed exploit that. All right, yes, it's a merge join again. And indeed it uses a merge condition as expected. It uses an explicit sort on the one side. Okay, we have expected that. But it's indeed using an index scan on the many side. The system has indeed seen that this scan will deliver the rows in ascending C order, because we are confined to a single A group. Inside that A group, C order, and this is exactly what the top level merge join requires. Perfect. Okay, So a careful consideration of the order of rows that flow in from these subplans can really bring a benefit for merge join here. Okay. Well, if you recall our discussion of the lockstep advancement of pointers in the left and right inputs, then you will recall that we had the requirement to be able to reset the read pointer in the right hand side input only if locally. Okay, so this has to be supported, resetting the pointer in the right hand side, and the subplan on the right hand side has to make sure to enable such rescanning, such resetting. There is a number of operators, of Postgresql operators, that can support such rescanning, that can re-emit the output that they have already delivered and, well, re-deliver that output again to the merge join. There is some such operators, for example, an index scan. An index scan is built in such a way in Postgresql that it can reset its read pointer in the sequence set chain, reset it to one particular point, and then start the sequence set scanning again from that particular point. So rescanning is possible if the input is an index scan. Okay. There's also other operators in Postgresql, operators that generate in-memory buffers of rows. For example, a sort operator that has been entirely performed on an in-memory buffer. An in-memory buffer that has been sorted by quicksort can support the placement of read pointers that can be easily reset to the top of the buffer again, or to the mid, somewhere in the mid of the buffer again, to rescan a particular portion of the buffer multiple times. So index scan and such in-memory buffers, maybe resulting from a quicksort operation, they can support such resetting of the right-hand side input pointer. If the subplan otherwise cannot support such a resetting, well, then the system has to make sure to establish the resetting ability in some other way. And the system that the method that Postgresql applies here is placing an explicit materialize operator above the right hand side input pan. So in such situations you will find a setup like this. You will find the merge join operator at the top and some subplan on the left. Of course, this subplan would deliver the rows in the right order. No resetting necessary in the right hand side input, but resetting might be necessary in the right hand side input. If this subplan cannot support such resetting on its own, well, then add an explicit materialize operator on top of this subplan to make sure that such resetting is possible. The materialize, if you recall, generates a tuple store, a rescannable tuple store that allows for pointer resetting. Okay. Well, let's see whether we can see this behavior over on the Postgresql side of things. Okay, yeah, so let's prepare the experiment. We will shut off hash join again, because merge join is everything that we are interested in now. And well, let's look at the current available work memory. And that work memory is the default of 4 megabytes. 4 megabytes is okay, but it's not considered to be super large. So for some operations, thus the in-memory work mem will not suffice, and we have to employ temporary disk storage. And this is, for example, the case for external merge sort. And if we look at this particular situation here, you will see that the right-hand side input of this equijoin here, the many side, will contribute its rows based on a C column condition here. And there is no index support for this join column. There's no index on the many table that has column C in its prefix. Okay, so there will probably be an explicit sort operator that will make sure that the many rows arrive in C order. And since working memory is not plenty, it's 4 megabytes, we will probably see an external merge sort applied to this, I think it's 500,000 row table, many table on the right hand side. Let's see the consequences. Okay, so let's first check the top of the plan. Indeed, it's a merge join based on the correct join condition. Okay, well, the one side, perfect. It can contribute its row in A order by just using an index scan, the primary key index that has been established on the one table. That's perfect. So that's a check on the left-hand side join input. How about the right-hand side input? The many rows have to arrive in C order. Well, we have to establish this C order using an external merge sort, as you can see. So we are scanning the many rows. All of these are fed into an external merge sort, of course, based on the key C here, and it will produce the rows on the single external single run that will be produced by this sort order. Such a run is not rescannable from the viewpoint of the merge join. As it occurs on the right hand side input here, it will be materialized. It will be materialized into a tuple store that allows for the rescanning of the input. And well, this is what exactly is happening here. Right. So now let's increase the working memory and let's set it to 64 megabytes. So in this particular example, this will change the picture in the sense that we can do away with external merge sort and instead build on internal quicksort based evaluation of the sort operator. Okay, otherwise this query has not changed at all. So let's re-evaluate it. Okay, this went a bit quicker, so everything stayed the same. Indeed, the index scan is still applied to the one side here. That looks good to me. On the right hand side, we are looking at the scan of the many table that feeds its row into an explicit sort based on the C column, but indeed we can use quicksort here. We can use quicksort. The quicksort will use 51 megabytes of the 64 available megabytes. That's sufficient. So we can indeed perform quicksort in memory. This will deliver an in-memory buffer of rows that can indeed be rescanned. Okay, and no need for materialize operator on top of this sort. The merge join can reset its repointer inside the memory buffer delivered by this quicksort, and this is all we need to successfully evaluate the merge-based join on top of the plan. All right, let's reset all the parameters here so that we are not surprised on further experiments. Okay, one final bit in our discussion of merge join in this video, and that would be concerning the output orders, the orders produced by merge join. Okay, so we were looking at the interesting orders in the upstream plans, in the child plans, in the sub plans that are feeding their rows into the merge join. Now we are looking at the interesting order of rows in the downstream plan, that operations that follow merge join. Okay, so well, if this merge join is embedded in a larger query that may have order by or group by clauses, well, then we may be lucky, and these order and group by clauses may ask for an order of rows that is indeed produced in a guaranteed fashion by our merge join. That could make an explicit sort operator completely obsolete. All right. Of course, other order-dependent operators could also benefit from this guaranteed output order produced by the merge join. Maybe other merge join operators could benefit here. Indeed, this may reduce the overall plan cost. We may even decide to switch from, say, a super cheap hash join. Hash join is the join operator, the member of the join algorithm family that we haven't discussed yet, but will discuss in upcoming videos. So maybe it's even worth to do away, to not consider a very cheap hash join and instead plan for a bit more costly merge join, only on the basis that the merge join can deliver its row in a guaranteed order. Hash join, as we will see, cannot deliver that guarantee. Okay, so maybe it's even worth to use a plan that is locally at the join operator a bit more costly, but will deliver rows in an interesting order, interesting to subsequent downstream operators, which will then be significantly more efficient to evaluate. Okay, and well, yeah, merge join can deliver such interesting guaranteed orders of outputs. Nested loop join can do this as well. So both of these are to be considered in this interesting orders scenario. Hash join, as we will see, cannot promise row order at all. Okay, and as we will see, indeed, PostgreSQL plays with the interesting orders and tries to save effort here. Okay, so let's see one final example in this video. Okay, well, here's a query that indeed is, again, an equijoin situation. It's an equijoin on this one and many table, and as you can see, it's based on the A columns, of both tables here. I have not disabled hash join at this particular point, and as you will see, well, this plan will indeed be evaluated using a hash join. Hash join delivers its row, as we will see, in any arbitrary order. Well, okay, since this query does not ask for a particular row ordering in the result, well, of course, the system will pick the cheapest join operator. It's indeed the hash join in this particular case, and and that's the right thing to do, of course. Okay, so let's see. Yeah, indeed, there's already the hash there, but we can see that the top level of the plan is indeed implemented using a hash join. As I told you, details coming up in the upcoming videos. Okay, so that's perfect, and that's perfectly fine. But things change if we embed this join operation, this equijoin operation, in a larger plan, in a slightly larger plan even. Look here, is just an added order by clause that we have added to this overall plan. And the order in which we request the rows to be sorted coincides with the join predicate here. This join predicate, if it would be evaluated by a merge join, asks for rows in A order, all right? And this is exactly the order that this order by clause requires. So if the rows would be joined using a merge join algorithm that can deliver rows in A order, well, then this order by would be a no-op. It would be a complete no-op, right? So we have to join anyway. Why not do it in a fashion that delivers row in an order that is interesting to the rest of the query and will lead to no-ops in the downstream plan? So let's see whether this order by can indeed change PostgreSQL's mind, and let's see whether it switches from hash join to merge join. Okay. Oh yeah, that looks not too bad. Indeed, 2 index scans are involved now. Indeed, there's a merge join here on top of the plan. You see that there is not a single mention of any ordering or sort operator in this plan. The merge join itself delivers the rows in the desired order. Well, it does so based on the A order that could be established by these 2 index scans on the one and many inputs. Everything flows into the merge join in A order. We do our lockstep synchronized scan of what the index scans can deliver, and we will deliver our output in A order, which is just the interesting desired order at the top of the plan. Perfect. So there's a very interesting interplay of the different SQL clauses here, the order that they require or that they produce, and to find the best constellation of operators in all of these situations, or in most of these situations. in most of the situations where we freely combine SQL clauses and the expressions here and the join criteria or the join conditions, this would be the task of the query optimizer, which is of course worth an individual chapter. All right, but merge join plays its role in this puzzle. Okay, so so much for these additional bits on merge join. I think there is one more merge join video ahead, and then it's time to switch gears and talk about hash join. All right, see you then. Bye bye.